Welcome to our webinar today, Drive Collaboration, Efficiency, and Growth with Advanced Planning and Scheduling Solutions. Questions will be answered live at the end, but please go ahead and enter them in the chat as they come up. Our presenter today is Mike Hunter. Mike has worked in digital transformation for manufacturing for over a decade, delivering smart manufacturing solutions and planning and scheduling, MES, IIoT, and analytics to customers in a wide variety of verticals. The is now yours, Mike.
Thanks very much, Vicki, and welcome everybody. We thank you for joining us today. Again, as Vicki said, my name is Mike Hunter, and I'm the Director of Digital Manufacturing Solutions here at Prolim Global. I spent the first half of my career in manufacturing leadership positions, mostly in heavy equipment, aerospace, and in consumer products goods. And for the last 15 years, I've worked in manufacturing, consulting, and software development. So let's get into today's agenda. We'll take a couple of minutes just to talk a little bit about Prolim and who we are as an organization. We'll kind of set the foundation for the demo part of the proceedings by talking about the enterprise value of production scheduling. I want to talk about the difference between a true APS, multi-constrained, finite capacity scheduling tool versus traditional planning and scheduling that we usually see in ERP and MRP. Then we'll go through some live demos of our advanced scheduling products and hopefully have a little bit of time left over for Q&A at the end. So real quick, Prolim, we just celebrated our 20th anniversary. We have 15 locations around the world, over 600 employees, over 1,700 customers. We are ISO 9001 certified. We are global partners with Siemens, AWS, Microsoft Azure, Snowflake, as well as many others. And again, our headquarters is here in the US, and we have offices around Asia Pacific region and in Canada and Europe. If we look at the different parts of our digital transformation consultancy, it's really divided into 6 parts. The digital manufacturing group, which I run for the team, really focuses on the digital thread for manufacturing, including scheduling, MES, CAM, IoT interactivity, production digital twin, and supply chain management. We also have a digital engineering practice, which focuses on Siemens NX and Solid Edge solutions. Our collaborative product development team primarily delivers solutions through Siemens Teamcenter PLM. As I mentioned, we're also partners with AWS, Snowflake, and Microsoft Azure as part of our cloud AI data and security team. Our professional services group offers consulting and implementation and digital transformation for all of the products that we sell. And we also have a large Siemens Mendix team, which delivers rapid application development. So let's kind of start out today. Why is scheduling important? A lot of traditional thought leadership and conversations I have with people will sometimes pigeonhole scheduling into just an execution tool. But from my perspective and in my experience, it can really drive value across your enterprise. Starting with new product introduction, scheduling is a key part of, Scheduling is a key part of driving collaboration with engineering and PLM, making sure that products are executed the way that they were designed, and giving feedback to the engineering team when there are issues with the manufacturability of those products. From the commercial side of the business, as a salesperson for a long time, most people in sales think that any sale is a good sale. But I would say that if you don't understand your actual capacity, there are sales that can get you in trouble. If you don't know if you can deliver a new product type, or onboard a new customer from a capacity perspective, that's going to bring a lot of trouble into the organization, because not only are you going to struggle to service that customer, but you're also going to struggle to keep your existing customer base happy. So APS brings a lot of value when we bring in forecast orders to the schedule, when we bring in a new book of business, whether it's a new customer for existing products or an entirely new product line and a new customer base. We can simulate what our production schedule and what our production capacity looks like when we bring those orders in and compare them and run them alongside our existing book of business. From a financial perspective, many of the customers we work with really struggle to understand their actual costs from a material perspective, from a waste perspective. When decisions are made on the shop floor to manufacture products in a different way, how can you really track the profitability of those items, and how can you ladder it back to the cost that you expected when you designed it? So we look at three layers of cost: the cost as designed, the cost as scheduled, and the cost as executed. More traditional value is obviously brought in manufacturing execution. So we're trying to put our customers in a position to succeed by giving them schedules that are achievable and really take into account all of the constraints in the factory before releasing them out to the floor. The other aspects where we have a huge impact are quality and maintenance. Many of our customers have manual quality systems or disconnected quality systems. APS can bring those systems into an integrated environment where quality activities are scheduled and executed alongside production. And maintenance tells us a similar story. Unplanned maintenance, particularly, we see a lot of disconnected systems in our customer base, where people are trying to get work out the door and unable to do so because maintenance has requirements that they have to take care of. And when those activities are not connected to a master production schedule, we see a loss of efficiency and a loss of productivity. So to me, scheduling really sits in the middle of the enterprise. It affects people from product introduction, sales, customer service, financial, everything that's happening in your organization. So what do we mean specifically when we talk about siloed information? Here's an example where we're looking at 4 different teams from design, manufacturing, engineering, execution, and services after the sale. And the questions these teams are trying to answer are: what should I build? How should I build it? How was it built? And how is it being maintained? And traditionally, we see siloed data and siloed teams without the real ability to look at all of those data sets together to bring value to the organization. So when we execute this digital thread, we're able to connect those teams with common databases that they can all look at and understand true cause and effect, and get themselves into a closed loop manufacturing situation where they're able to look at all the data from what they built to how it's functioning in the field for a more successful operation. So a quick look at the digital thread for smart manufacturing within Prolim. We really see it as 4 pillars for best-in-class manufacturing, which would be planning, execution, connectivity, and optimization. And we're going to see more examples of this when we get into scheduling, but scheduling gives us a true understanding of capacity, not just based on the availability of machines or lines, but also available labor, tooling, physical constraints, material availability. It's also a collaborative tool, again, that we can bring production and sales together, modeling real simulations that show the actual production scenarios that we can model, looking at multiple constraints. Once we've created schedules that are efficient, feasible, and achievable, we release that out to our next pillar, which is execution. So MES is going to take that schedule, collect all the data from the floor. It's going to monitor material consumption. It's going to provide electronic work instructions. It's going to be our quality execution that we've outlined in the scheduling process. From there, we're connecting to machines and lines on the floor. So we're bringing operational data into the mix by and contextualizing it with our expectations from a manufacturing standpoint, and offering customers real-time monitoring of their plant conditions. And finally, when we have all those things brought together, from an analytics perspective, we can optimize the process by combining all of that data and giving our customers actionable KPIs. Oftentimes what we're hearing from customers is they're generating a tremendous amount of data from the floor, but it's not actionable. They're trying to go in after the fact and figure out what happened. And that data is often at a volume that is not manageable. And again, it's not contextualized to expectations in the planning and execution aspects of the operation. So where does scheduling fit in a traditional, in a digital factory scenario? In best-in-class operations, we're taking data from PLM and engineering. We're taking data from ERP, which is going to be our work orders with routes and bombs. We're taking demand from our customers. We're taking information about purchase orders and inventory levels. We're pushing that into the scheduling engine to provide an actual multi-constraint schedule that's feasible. And then we're releasing that out to the MES system. We're also bringing in quality planning. So whether we have laboratory activities, whether there's nearline or at-line sampling, or actual quality operations that are happening in parallel to production, that also gets put into the schedule. From there, we're executing at MES, we're executing in quality, whether it's on the floor or in the lab. We're also integrating shop floor data, maintenance, warehouse data, and logistics and operational data that's providing our inbound raw materials and any interplant transfers that we have to do. So why is scheduling difficult? A lot of people we talk to would say, well, it's just a schedule. It's not that hard. Well, let's consider if I had one machine or one line and I had 5 different operations that I had to complete, that's 120 different combinations of sequences that I could come up with to run those operations. If I just double that and say, now I have 2 machines or 2 lines and I have 10 operations, that number increases exponentially to 14,400 different combinations. But those 14,400 only consider 2 machines with 10 ops. What if we also consider all the other things that we see in a real world production facility? What if we have variable setup and run times per machine? What if we have machines that only have specific capabilities? They might not be able to run every type of material, every size of material. What if we factor in qualified operators and how many of them we have available? What about the availability of tooling or physical space constraints? And then what if we have dozens of machines and thousands of operations, as we most often find with customers we work with? Once you add in all of these factors, we're getting into hundreds of millions of combinations potentially. So scheduling is a difficult problem. And the tools that we see customers typically use, ERP, MRP, Excel, can work for a while, but once the business really starts to scale and grow, those tools become obsolete and become a limiting factor in the growth of your company. So let's talk a little bit about the 5 most common scheduling problems we see in manufacturing. Having sold and implemented APS for over a decade in a variety of situations, the first thing that most of our customers will say is, well, we're not like anybody else. We're unique. We have problems that nobody else has. But having implemented the system in just about every vertical you can think of, from food and beverage to rigid plastics, roll goods, metal processing, heavy equipment, we really see 5 common problems. And those are the problems that we're going to walk through in the demo today. The number one is primary resource modeling, and we'll get into the details of that a little bit later. Material availability, and that's purchased raw goods that we see coming in and having in stock, and also intermediate or sub-assembly goods. How do we allocate those goods to make sure that we have an achievable schedule based on the availability of those materials? We also see sequence-dependent changeovers, and there are a vast number of examples that we can talk about, from allergens and ingredients to ink colors to resin colors to tooling to material. All of those things can affect the amount of time it takes to change over a machine. We also see a variety of secondary constraints, and we'll get into the definition of that a little bit more deep later on. The secondary constraints are going to be other factors that limit your ability to produce. That could be qualified labor, it could be tooling, it could be physical space. And the last thing we see are time phase issues, which time phase issues really encompass a couple of things. Number one, can I start another operation before the previous operation is completed? And if so, what are the rules that allow me to do that? And what about wait times and buffers? Can I immediately start the next operation, or are there factors that would make me have to wait? Typically, we see this with heat treatment or ovens, a lot of roll goods where we have additives that have to cure, like glue or adhesives, or different coatings that have to go on a product. Sometimes those things can't be moved to the next process for a period of time. So pretty much everybody we talk to has one or all of these problems, and somewhere in between. So we're going to walk through each one and talk about how APS addresses those issues. So first off, let's talk about primary resource modeling, and let's talk about the difference between traditional ERP, MRP, and a really robust APS solution. ERP, MRP is primarily work center driven, and what I mean by that is if you have multiple operations like cutting, forming, welding, slitting, painting, whatever the case may be, you'll have a work order from your ERP with a route, and each step on that route is based on a work center. And that work center is based on a certain type of work, and it has a fixed hourly cost. What MRP doesn't do very well is model at the machine or resource level. And to get around that, customers usually set up multiple routes in their system. So what do I mean by that? Well, let's say I have a cutting work center in my plant, and I have 5 different cutters. From ERP, MRP's perspective, all of those cutters are the same. They can run the same orders. They take the same amount of time it's the same cost to set them up, the same cost to run them per hour. And it doesn't understand the idea that those cutters could be different. I might have 5 different cutters, but some of them might be 10, 15 years old. They might be really slow. They might take a long time to set up. Other cutters might be brand new. The setup is more automated. The throughput is higher. In addition to that, those cutters might have different attributes. Maybe some are wider than others. They can handle thicker material. They can handle different types of material. They can handle wider and narrow materials. ERP, MRP doesn't really make the distinction. It just lumps them together into a work center. So typically what customers try to do to get around that is create multiple routes, and they'll create individual work centers for cutter number 1 and cutter number 2 and cutter number 3. And the maintenance of those multiple routes is cumbersome and virtually impossible to keep up with in a high volume facility. And oftentimes, once an order is released through MRP, if it's assigned to the first route, if you want to change it, you have to cancel the order and start over. So we see people struggling to keep up with a dynamic production environment. APS, on the other hand, models at the resource level. So we understand everything about those individual resources, the differences between them. We can assign them and select them based on product attributes that we get from PLM or our design systems. We can model resource-specific run times and setup times. We can also support batch processes with finite and infinite modeling. So a finite resource is one that can only run one operation at a time. An infinite can run multiple. So let's jump into our demo real quick, and I want to get specific and show you what I'm talking about. So this is a very basic model. We don't have a lot of operations in it. We intentionally want to keep it simple to illustrate some points for you. So this is a Gantt chart. If anybody's ever seen one before, it's pretty typical. We've got our machines or resources down the left-hand side, and we've got time moving forward left to right across the top. You can see that we have different types of resources. I've got 2 cutters, 2 forming machines, 2 machine centers. And in this case, I've also modeled people as a resource. Another thing that's more flexible about APS than MRP is that we can pretty much define anything we want to as a primary resource. It could be a physical area for assembly. It could be a person that's doing that assembly or inspection or testing procedure. Or it could be a single machine, or it could be an integrated line that's running multiple operations in sequence in a nonstop fashion. So that's our basic Gantt chart. We've also got our editor window. So typically these are our work orders with different operations that need to be processed. We've got a work order number. We've got the component we're making. We've got the different processes, cutting, forming, and machining in this case. Every time we implement a product, this is going to be integrated to your ERP system. So we'll just pull these work orders out of the MRP, out of the run that you've done. So let's just pick one order and put it on the schedule. I'm just going to pick this one order and I'm going to put it on the board. And if we go back to the Gantt chart, you can see that I've got 3 operations here. I'm going to start in cutting. I'm going to go to forming, and then I'm going to go to machining. And you can see I don't have any wait time and I don't have any transfer overlap. We're finishing one operation and moving on to the next. I can easily drag and drop these around if I want to based on my resource group definition. So if I want to move this order to the other cutter, you can see I can do that. If I want to move a cutting operation to forming, it won't let me because it's not part of the resource group, because that's not the machine that I need to do that work. So first off, we can see one thing. I can see that cutter number 2 is slower than cutter number 1 because the time I'm scheduled to take is taking longer. Just by dragging and dropping, it's dynamically updating when I do that. So if we go back to our data real quick, we can look at resource groups, and I can pick this process and look at the resources in this group. In this case, I've got cutter number 1, I've got cutter number 2. One of the big advantages to APS is that I can have an unlimited number of resource groups. So in this case, this resource group that the operation is assigned to is telling me that I always want to run on cutter 1 if I can complete the work on time. If cutter number 1 is booked and I'm going to be late, then go look at cutter number 2. I might have another product where I'd prefer to run on cutter number 2 as opposed to number 1. And in that case, I could just move these around in a different sequence. In a bigger operation or a bigger play, if I had 5 cutters, we might say, I want to limit it by the width of the product because only a couple of the cutters can run maximum width material or thicknesses or different types of material. So we can create as many of these hierarchies as we want to within the resource groups. And typically those assignments are made by data that's coming from PLM and engineering to support the work orders that we get from ERP. So I'm going to take these off the board and let's schedule the way that somebody would normally schedule, which is we're just going to, in this case, use a forward sequence. I'm going to automatically schedule the entire plant. You can see I scheduled the whole plant in just a few seconds. And you can also see that I have some different colored blocks here. In this case, I've got different order statuses. So anything that's green is going to be a planned order. Those are confirmed orders, and these are suggested orders. Now, this is very helpful if we go back to our interaction with the commercial side of the business. We could bring in suggested orders based on a brand new customer, and we could schedule all of our planned and confirmed orders first, and then we could put those forecast orders for a new customer on the board and see if we can actually handle it from a capacity standpoint. Again, every time we run a schedule, we're not actually releasing anything to the floor. These are all simulations, and I can make as many schedules as I want, and I can save them and do whatever I like with them. And once I agree on the schedule that I like, then I can release that out to MES for execution. So we have a lot of power to model at the resource or machine level, as you can see. Another thing you'll notice is that all of these resources are set up as finite, which means I can finish one or I can start one order. When I finish it, I go to the next one and so forth until I'm done with my work. We can also set up what's called an infinite resource. So I'm going to jump out of this model real quick into another one. Not going to save anything there. Let's go to this model, which is a little bit more complicated. We've got more orders here. And you can see in this model, I've got more resources. I've got a prep area, manual welding. I've got a 5-axis CNC. I've got a separate prep area, robotic welding, more CNC machines. We've got an assembly area, ovens, painting, finishing, testing, final inspection. Again, this is where, from a testing and inspection standpoint, we can bring all of our quality planning into the system and turn it into quality execution so we can monitor our ability to achieve those tasks as well. So I'm going to do the exact same thing. I'm just going to forward by due date. In this case, I'm not trying to be efficient. I'm just saying take the first order that's due and put it on the first resource that's available and continue that process until everything's scheduled. Now, again, we see a lot more orders in this model. But if we look at some of the resources that we have, we can see in the ovens, in painting, finishing, and testing, we've got more than one order running at the same time. So these are infinite resources as opposed to finite. So we can model this by assigning that resource as infinite and then constraining it with another rule. So for example, in an oven, we might say any items that have to be put into the oven at the same temperature for the same amount of time can be put in at the same time. We could add a second constraint, maybe based on weight, maybe based on physical space, to say, hey, at any given time, I can only put 100 pieces in that oven, or I can only have 4 work orders in that oven. Looking at testing, we could make the constraint based on qualified operators that are able to do the test. So in this case, I think at most we have 5 different testing operations at once. We could limit that by saying I have 5 different test or lab equipment people or lab staff that can actually do that work. So I can never be testing more than 5 things at a time. So just to reiterate there, that's one of the huge differences between APS and ERP and MRP is our ability to model at the resource level, to understand machine capabilities and attributes, to understand batch processes with finite and infinite modeling, and to model specific runtime and attributes for each one of those things. Let's go on to our next one. Material availability, both raw and intermediate. Most ERP, MRP systems that we see, they're able to do an initial allocation, but they really struggle when things change. And when the schedule changes or there's anything happening on the floor, which anybody who's ever worked in a plant in their life knows that things change about every 5 minutes, ERP, MRP struggles to respond to that change and understand cause and effect. And so oftentimes, particularly with subassemblies, we see customers struggling to understand if they have enough subassemblies for all of their finished goods. APS, on the other hand, can create end-to-end allocations from inventory to purchased orders to subassemblies in stock to finished goods to final demand. And we can even write advanced material allocation rules that are configured to support whatever your requirements are, and we can enforce those rules out on the floor. So let's go back to our model. Let me get out of this one and go back to the original, more simple model. Oh, sorry about that. Let's go back to this schedule. And I'm going to sequence everything one more time here. So again, we're just going to say first come, first serve, forward sequence by due date. And we've scheduled the entire plan. If I want to take a look at these orders, we can see hierarchy from start to finish. So if I want to say, I want to highlight all subsequent operations here, we see a few things. One thing I didn't cover when we first looked at the Gantt chart was this top row, which is supply. You can see all of these diamonds that appear are purchase orders coming in the future. It tells me what's coming, it tells me how many are coming, and it tells me the date that it's coming. At the bottom of the Gantt chart, we have all of our demand, and demand can take any form that we can consider. It could be a direct sales order to our customer. It could be a transfer order to a distribution center or another plant. It could be a forecast order or a safety stock order. It's whatever demand your form of your demand takes. So in this instance, we see we have one order here with cutting, forming, and machining. And in turn, those orders are going to be consumed by finished good orders. So John here is going to assemble this one. Tom has another one to assemble that's coming from that same subassembly order. And Mike's going to assemble this order. And all of those are going to go to our final demand. And if we look at that in our Material Explorer window, we can go all the way from start to finish. So we can see that at the first operation, operation 10, we need 180 pieces from stock. We're getting 170 from out of stock, and we're getting another 10 from this purchase order. Once those items are produced, there are 3 assembly work orders that are going to consume those items. So that shows us end-to-end what's happening. Now, let's simulate something that changes, because this is always the downfall of ERP, MRP systems, is their ability to respond to change. You can see that this order is not scheduled to run until this date because it's being supplied by this PO. And if I want to take a look at this order, Now, typically, this would be an integration with an ERP system. So all of our purchase orders are coming over live from the ERP. So any changes to those POs are going to automatically be reflected whenever you reschedule. But since I'm in a standalone mode here, I'm just going to simulate a change. So let's say we knew that we had 300 of these coming. We know that they're due on November the 2nd. Let's say our supplier called us and said, hey, we had a quality issue. We've got to rerun some of your parts, so you're not going to get it until the 10th. Again, where normally this would come from ERP, but I'm going to do it manually here. Now I can see that that purchase order is out here and that the line linking it to this operation is red, which means it's impossible because I can't start till I have it. So we have a button here called Repair Schedule, which basically resynchronizes everything that's happening. So I'm going to repair the schedule based on my new purchase order information. And we can see a few things happen here. Not only did this work order move out to accommodate the late PO, but all of the sub-assembly orders, all three of them, moved out completely synchronized with the availability of that product for assembly. So this is a simple example. It's one PO with one sub-assembly order and 3 finished good orders. But in the real world, this could be a huge problem. We might have 10 different items on that purchase order, feeding 100 different sub-assembly orders. And those 100 sub-assembly orders could be feeding 1,000 finished good orders, which could be feeding 4,000 or 5,000 sales orders to our customers. So if you're trying to do this with Excel, it could take you a day or more to figure out the cause and effect of that purchase order being changed by just a week. So again, this is where we have a huge advantage over ERP, MRP, because we're able to deal with change and we're able to see cause and effect immediately on the shop floor and react to it and do something about it. We can also create custom rules for our material consumption. So if we wanted to say that certain lots or certain serial numbers of product need to be attached to our work orders, we could do that too. We could also create rules that talk about location. So we can work with your warehouse management system to make sure that we're getting products from the right place to the right work orders. And once they're done, once that's done and released out to the MES system, we can enforce those rules on the shop floor. So let's go to our next main problem. Sequence-dependent changeovers. Typically in ERP, MRP, there will be a setup time field for every step on your route. And again, it's going to be assigned to a work center. But most of the time, that setup time is based on a full changeover. It has no idea what the disposition of the machine or resource is before you start that operation. There's no link to what's currently running there. With APS, we can take that and make it dynamically changeable setup time, and we can break it down into multiple constituent parts. We can also automatically update the schedule whenever we change the sequence of operations, and we can also create configured scheduling rules to drive efficiency. So let's go back into our model, and I'm going to do the same thing I did before. I'm just going to forward sequence by due date, and when we do that, we see a couple of things. First off, it should be clear, these smaller black rectangles that you see on the Gantt chart, that's setup time or changeover time. The larger colored rectangle is actual run time to complete the operation. And you can see that I've got quite a bit of setup time, particularly in my cutting area here. And if I wanted to know how much, we have a basic schedule statistics button that we can take a look at. And it's got some high-level KPIs for the schedule. And we can see that right now I have 17 days of setup time in my schedule, which is a lot. And I might not like that. I might think that I can do better. So how would I do that? I can take everything off the board and I can resequence it. And now I'm going to use a basic out-of-the-box APS rule called minimize overall setup. And I'm going to schedule again. And now, instead of just a first come, first serve, it's trying to group orders together to have the minimal amount of setup possible. And you can see just by looking, there's a lot fewer black rectangles on the schedule than there were before. And if I go back to my statistics, I've gone down to 2 days of setup time, which is a significant savings. So how does the system do this? Before I show you that, I'll also show you we can drag and drop these orders and the setup time will change dynamically. So let's say I decided to run that between those two orders. Not only did it generate setup time going into that operation, but now there's setup time going back because I'm making more changes to the system. And I can undo that operation if I want to. You can see that setup time goes away. So how do we do this? If we go back to our data, we have what's called a changeover group. And we can assign this by machine. We can assign it by work functional area of the plant, however we want. And in this case, I have multiple attributes. And right now I've just told the system, whenever this attribute is not matching, it's going to be 1 day and 12 hours of setup time. If I wanted to get, and I can have as many attributes as I want. So for example, if I said that changing the raw material is going to cause a setup time penalty, I could just say any change to material, the actual material type, is going to give me a setup time of 3 hours. I could also say that changing the material width adds another 2 hours. I could say that changing tooling adds 2 hours, and the system will automatically calculate this and give me the total of each one of those changes. And I have an unlimited number of attributes. So if I wanted to be more specific, I could create a matrix. So in this case, I could say going from size 1 to size 1, no penalty. From size 1 to size 2, I could have an hour. But from size 2 to size 1, I could have a different time. So most often we see matrices with color changes. This is very common in plastics, for example, where I'm running different colors of resin. So going from white to black, for example, would have a shorter setup time than going from black to white. Because if I'm going from black back to white or any darker color to a lighter color, I have to completely flush the system. It's going to take me more time and it's going to cause more waste. The other common use case we see is in the food and beverage industry. We've got a lot of implementations in food and bev, and our customers, if you look at any ingredient panel, any claims that are made by those manufacturers saying, this is gluten-free, this is dairy-free, this is nut-free, this is kosher, this is halal, this is organic or non-organic. When we take all of those different attributes, it changes the amount of wash down and cleanup that they have to do. So we can put all of the different allergen formulations into a changeover matrix, and we can sequence those lines as efficiently as possible. So let's move on to our next main scheduling problem. And that's going to be secondary constraints. So by definition, in APS, the primary constraint is going to be the resource. Again, that's a machine, that's a line, that's an assembly area, it's a cell. It's the main, it usually aligns with the actual steps on a route. But secondary constraints can be anything else. So do I have qualified operators? Do I have necessary tooling? Do I have physical space? So for large equipment manufacturers, sometimes they have testing or final assembly. They might only have 2 or 3 testing bays or assembly bays available at any given time. So obviously they can only be testing or assembling 3 units at once. And we would manage that with a secondary constraint. So while ERP, MRP, sometimes you'll have tooling or operators on a BOM or a route, not all the time, depends on the system. They're never considered as a capacity constraint. ERP, MRP only considers the primary work center. With APS, there's an unlimited number of constraints that can be applied. We can also model them as a hard or a soft constraint, which I'll talk about in a little more detail. So let's go back to our demo. And let's take a look at secondary constraints. Down below here, we've got a plot window. And in this example, we're talking about qualified operators. So constraints can be assigned at the machine level, the resource group level, or the work order level. And in this case, you can see that I am using 2 operators for cutting, and I've got 2 available. So as I move from left to right, you can see the orders above being highlighted. You can see that here, I'm not using any. We can model it to have setup crews. So a constraint might only be used during setup time, and we can have operators only available during runtime. So here you can see I've got setup time on cutter number 1, but I'm not using an operator until I go back. So as we go through the system, we can see I've also got operators for R2. So these are my forming operators, and you can see how many I'm using at any given time. So how do we simulate that when we have changes to the amount of operators that are available? Let's go ahead and schedule again, forward by due date. And let's look at our calendars. For R1, which are our cutting operators, this is my calendar, and I can change it for the long term, for the short term, or even for a day or two if people call out sick, or if I have somebody going on vacation. So right now, let's say I only have one person that can run that line. Now, when I look at my plot window, you can see at all these times where I'm in red, I don't have enough people to do this. I only have one person, and the system is telling me we're scheduling for both. So you can see when I violate the constraint. And we can go back over to, and you can see also on the cutting side, we're running constantly here, right? I can go back to my helpful repair schedule button and say, hey, I've changed it to one operator. What does that do to my schedule? Now you can see that I've taken that constraint into account, and I've only got one operator, so I'm never running more than one machine. And in fact, that operator is hopping back and forth from cutter 1 to cutter 2. So I can see a true example of my capacity. In addition, we can manage the same thing with tooling. We can manage the same thing with physical space. We can even manage it for energy. We have an energy constraint here. You can see when we assign power consumption for each machine, we can see how much power we're using at any given time. We actually have one customer that's in a small town in Texas, and they use more electricity than the entire town. And there are times when the city will come to them and say, you guys can't run 24 hours a day this weekend because there's a power limitation. So we can actually help them build a schedule dynamically that says, hey, this is all the power that we have available. What does the schedule look like when this is being enforced upon us? So secondary constraints, very valuable, very flexible, and also key to really managing your actual capacity at a level that traditional systems aren't going to do for you. Okay, the last one that we want to look at, time phase issues, including transfer quantities and buffers. So again, ERP, MRP, there's really no functionality that allows you to overlap operations. There's no functionality that allows you to enforce wait times between operations. So within APS, we have a functionality called transfer quantity. The transfer quantity allows me to start the next operation before the previous one is finished. We can do this by quantity completed. So you might want to say, hey, as soon as I finish one pallet from operation 1, I'm allowed to move that and start operation 2. Or you might be making them by batches in operation 1. So as soon as I get a batch or a lot finished, I can go ahead and start. Conversely, we can enforce wait time. So again, if we've got heat treating operations, if we've got coating or powder coating operations that things need to cure or cool before the next step, we can enforce wait time between those operations. So let's go back to our model one more time and just show an example of that. And get out of this one, back here. We'll generate our more complicated schedule here real quick. No, let me take that one. So in this model, we've set up a couple of examples. I'm going to highlight an order here so it's a little bit easier to see. I just want to highlight all subsequent operations. So you can see that when I go from finishing to testing, and I'll zoom in so you can see a little bit better. You can see I've got an overlap to where testing is starting almost at the same time as finishing. So we've got a transfer quantity in effect for that. In a similar one, when we look at assembly and oven, we can see that we have a gap between those things. So if I look here at the attributes, oh, that's not the one. I have a field called slack time before next operation, and it's set to 1 day. So it's never going to let the next operation start until a day has gone by in between. So a simpler example than maybe some of the others, but certainly that's something that we see with a lot of our customers that they're not able to achieve with their traditional systems. So those are really the 5 issues that we see that are unique to an APS implementation. And I think we've covered the reasons why we think scheduling is a key attribute to best-in-class manufacturing, and how it speaks to all of the other divisions within your enterprise, from engineering to sales to finance, and how it can really change your capabilities across the enterprise. So with that, thank you very much for attending. I hope this was helpful, and I think we've got a bit of time, and hopefully we've got some questions.